Hello there, calculus class. Dr. Shragi here, and we are getting ready to move forward into the next section of the class. This is another one of those rules that I wouldn't have minded skipping actually all that much, although it is actually one of my favorites. But under the limited time we have and so on, I wouldn't have minded skipping it. But actually, I had messages from Ivy Tech that they do want you to make sure you learn about L'Hôpital's rule, which is our topic for today. I actually do not know anything about French. I don't know if that is, I've always heard it called L'Hôpital's rule. I don't know if that is in fact right as to how to pronounce it. L'Hôpital's rule is actually pretty cool. Make sure you get yourself a copy of the L'Hôpital's rule handout that's attached to the Google post, classroom post about this lecture. L'Hôpital's rule is for when you are working with a function that could be written as, well, it's a rational function. It has a numerator that's a little function up here, and it has a denominator that's a little function down here. I mean, we could write this as like an f of x over a g of x, where in this case the f of x would be sine x, and the g of x would be equal to x in this case. I mean, there's like a little function on the top and there's a little function on the bottom. That you can picture a million different things that would work for. In general, it's a happy little function. You can make it in Desmos. It looks something like this. I have it on page 1 of the handout. And just staring at it, though, it becomes clear that there is some problem here. What happens when x is equal to 0? Well, we've got 0 in the denominator, so you know you're not nuts about this. But then sine of 0 is 0 as well. This becomes kind of a 0 over 0 problem. Which is weird, because if you look at the graph, it doesn't actually, or on the front page of your handout, it doesn't actually look like anything goes all that bad. I mean, if you, as the limit, as x got closer and closer to 0, I don't see any reason here. In fact, this turns out to be the point 0, 1 right there. It doesn't look like anything so bad, although actually in Desmos, if you actually try to click on this point, it's going to call that point 0, undefined. Because it's recognizing that something's wrong here. Something is not right at this place here, despite the fact that actually it doesn't really look that bad when you look at the graph. It's sort of like there's a little hole in the graph right there at the limit, at x equals 0. And we could have a happy way of saying this here. I mean, while the value right there at x equals 0 is actually undefined, because it kind of blows up in two complicated ways, we could say that the limit as x approaches 0 of this function, right here, of this thing right here, well, that actually looks, I mean, just by looking at the graph, it looks like this should be a thing. In fact, it looks like, from our graph here, it looks like it should be 1. So we have this weird situation here where if we use direct substitution, we get 0 over 0, and 0 over 0 is not equal to 1. I mean, this is what's called an indeterminate form. Indeterminate form. No one really knows what 0 over 0 is, and yet we can tell by just looking at it that in this case it's going to be equal to 1. Well, turns out that in these situations with these indeterminate forms, like, well, if I just evaluated that limit, it would be 0 over 0. This is where L'Hôpital's rule comes into play. And L'Hôpital's rule, well, there's actually a couple of different ways we apply it. But L'Hôpital's rule tells us that if we have some kind of function where we have the limit as x is approaching some value a, like maybe it's approaching 0 or even approaching infinity, of f of x over g of x, if this is a problem that's getting us to the 0 over 0 form, like if we actually just use direct substitution and it's going to give us a 0 in the numerator and a 0 over denominator, weirdly, this is the same thing as f prime of x over g prime of x. That's actually what L'Hôpital's rule tells us. Now, that is not in general true. If this number, if we could just use direct substitution and like blah, 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 we just did it and, oh, this is equal to 3, and the denominator here, that's equal to 4, Oh, well then you don't use L'Hopital's rule anyway. We could just use direct substitution to evaluate limits the way we did like in February. But if you're getting yourself into one of those indeterminate forms, like 0 divided by 0, which nobody really knows what that means, you can actually take the derivative of the numerator divided by the derivative of the denominator, and that will work too. Holy smokes. Holy smokes. So in other words, in our earlier example here, where we were talking about the limit as x approached 0 of the sine of x over x, that, according to L'Hopital's rule, will be the same as the limit as x approaches 0 of the derivative of the numerator, which is cosine of x, divided by the derivative of the denominator, which is 1. Okay, now let's try direct substitution. Putting in just 0 in for x, cosine of 0 is 1. So this is just 1 over 1, which is just 1. Which is the answer we got down here. While the value actually at x equals 0 is indeterminate, get a little hole in the function there, the limit, whether we're approaching from the left or approaching from the right, is 1. We're getting closer and closer and closer to x equals, to the function being equal to 1. Isn't that weird? L'Hopital's rule is a weirdly useful tool. Surprisingly often when I was doing science and stuff like that, all of a sudden a L'Hopital's rule type thing happened. And, well, I mean, I never did pendulum, but I mean, like for example, sine x over x is part of the story about how a pendulum moves. And it looks weird when you're looking at it at the map, because it sure looks like at the bottom of the motion of the pendulum, when x was equal to 0, this should be blowing up to infinity, but in fact it doesn't, because by L'Hopital's rule. L'Hopital's rule is pretty cool, but we have to kind of see some examples of it to be happier with it. Let me clear some of this out. Alright, let's do, this is example 438b in your book. And it's asking you to find this following limit. The limit as x approaches 1 of the sine of pi times x over the natural log of x. Well, first off, I mean, if you didn't know what else to try direct substitution. Well, let's put 1 in here. Sine of pi times 1, sine of pi, oh, that's going to be, sine of pi is 0. Natural log of 1 is 0. That's a 0 over 0 indeterminate form. Well, that smells like L'Hopital. So, alright. L'Hopital's rule is going to be the trick here. So L'Hopital's rule says that we can take our original expression here and it will be equivalent to the limit as x approaches 1 of, okay, take the derivative of the numerator. It's a chain rule. Got an inside part and outside part. It's going to be cosine pi, pi times cosine, pi times the cosine of pi x, right? So it's a chain rule. Take the derivative of the outside times the derivative of the inside, right? And the derivative of the denominator, which is just 1 over x. All right. Well, that was our L'Hopital's rule step. Let's try direct substitution now. If x is equal to 1, this is pi times the cosine of pi. The cosine of pi is -1. So that's -1 times pi, which is negative pi. And the denominator, plug in 1. 1 over 1 is 1. So the answer is just negative pi. Huh. So the limit of this expression right here is just negative pi. Now, I actually on top of page 3 graphed this function. It looks a little, just sort of something just to be touching here, it looks a little something like this. And at the value x equals 1, if you go down here and made it in decimal, so you try to touch it there, it won't let you. It'll say undefined. But that value happens at pi. I'm sorry, negative pi. Right? The limit as we approached it, whether from the left or from the right, was pi. Well, that's kind of cool. Huh. Again, this looks awful. I mean, once you realize, holy smokes, that's going to be a 0 and that's going to be a 0, you'd have all kinds of reasons to be suspicious that this is going to be some kind of terrible thing. And L'Hopital's rule can get into really terrible things, as we shall see on page 3. But usually L'Hopital's rule is more of a solving problems thing than a causing problems thing. Let's do another one. This is 438D. I like this one because it does something that L'Hopital's rule problems often do. It's asking us to evaluate this limit. The limit as x approaches 0 of sine x minus x all over x squared. Feel free to think direct substitution. Direct substitution is always a good thing to try when you're doing a limit problem. But if I plug in 0 here into there and there, I'm going to get 0 minus 0 is 0 divided by 0. This is another 0 over 0 indeterminate form. We can't really do much of anything with this. All right. Well, L'Hopital's rule is going to tell us that that same function right there is going to be that same limit that we just had before. By L'Hopital's rule, we can switch it out and say instead of f and g, it's going to be f prime and g prime. F prime, let's see, we're going to have cosine of x minus 1, the derivative of this minus derivative of that, all over the derivative of this. Hey, great! I know when I think about these things, I want to think now about direct substitution. Let's see, cosine of 0 is 1, minus 1 is 0. 2 times 0 is, oh crud, it's still a 0 over 0 problem. It sounds like we have failed horribly, but actually we're okay. It is often the case on L'Hopital's rule problems that you end up having to apply L'Hopital's rule more than once. I don't know that I've ever seen even a 3 times L'Hopital problem, but 2 times ones like this are no big deal. All we got to do is just take it again. I mean, we know this form of the limit is giving us this indeterminate form, which means by L'Hopital's rule, we can go ahead and say, okay, the derivative of this divided by the derivative of this. Okay, what's the derivative of cosine? It's negative sine. Derivative of minus 1 is just 0. Derivative of this is just 2. All right? Another application. So we did L'Hopital's rule twice. L'Hopital's rule here and L'Hopital's rule here. Now, let's see what we got here, direct substitution. The sine of 0 is 0. And divided by 2 is just 2. So, all right, 0. So after all that work, our original limit is apparently equal to 0. I never have blind faith on these things. I always make myself a graph, and you can see my graph over there on the top of page 4. And it looks something like this. And if you actually, Desmos tried to click on that middle part, you find out it says it's indeterminate right there. But you can clearly see as we approach from the left, the limit as x got closer to 0 was 0. And as we approach from the right, as x got closer and closer to 0, our function got closer and closer to 0. So I buy it. I buy it. This seems good. Okay. Now, L'Hopital's rule is just about as handy as it gets. And it can do more tricks than you would believe. For example, the same rule that we have been using all along also works just fine. Okay, remember we had the indeterminate form 0 over 0? But another type of indeterminate form you could have is infinity over infinity. I mean, what does infinity divided by infinity mean? That's hard to know, and in fact can mean different things in different situations. But we have plenty of ways that we can apply L'Hopital's rule and on infinity divided by infinity problems. Let me give you an example here. This is 439A in your book. It's saying evaluate the limit as x goes to infinity of 3x plus 5 over 2x plus 1. Alright, now, if you just try direct substitution, it's a little weird to think about infinity and direct substitution, but it'd be 3 times infinity plus 5. Well, that's a big old number. And 2 times divided by 2 times infinity, it's just infinity divided by infinity. I don't know for sure what that means. So, but L'Hopital's rule is going to work for that. So L'Hopital's rule says that this original function that we have is going, because it's an indeterminate form, infinity divided by infinity, it's going to be the same thing as saying, instead of f of x over g of x, as being f prime of x divided by g prime of x. Well, what's the derivative of f, the numerator? It's just 3. What's the derivative of the denominator? It's just 2. So this is the limit of just a constant. That's just 3/2. Huh. Wait a minute. So let's make ourselves a graph of the function just like I did at the bottom of page 4 right here. And it's kind of a weird looking thing. Something like this. But as x heads out towards infinity, it gets closer and closer and closer to the value 3/2. Okay, I didn't draw it very well here, but it's asymptotically approaching 3/2. That's kind of cool. Infinity divided by infinity meant something there. Now, L'Hopital's rule can be applied to even more weird things. It's actually derived for those 0 divided by 0 or infinity divided by infinity cases, but in fact it can do all kinds of interesting tricks. One of the interesting tricks, by the way, yes, it's derived, and in fact your book goes through the proof of it, but we're just not going to do that, okay? YouTube does not need a video of us deriving L'Hopital's rule, and I don't need to do it or whatever. Another weird kind of problem that we can solve that is an indeterminate form is the 0 times infinity problems. I mean, 0 times any number means 0, but an infinity times any number is infinity, so what is 0 times infinity? It's another indeterminate form. It's not really defined what that means. So 0 times infinity, or 0 dot infinity problems. Well, turns out we just have to rearrange the problem until it looks like something L'Hopital can solve. And example 4.41 in your book is probably the best example I could think of as to how to do these things. It says evaluate the limit as x approaches 0. They're actually saying from the left here, just because as you'll see at the, well, you can even take a look at the graph at the bottom. From the right, from the right. From the left doesn't exist. That's outside the domain of the function. Of x natural log of x. Okay. If you just tried to use direct substitution, you're going to have plug in 0 here. You'll have 0 times the natural log is 0. Natural log of 0 is actually, it's infinity. Is it infinity or negative infinity? I can't remember right now. But, yeah, negative infinity. So, this is a 0 times, the answer is actually 0 times infinity. It's not really clear what this is going to be. But, if we could just find a way to write this so that L'Hopital's rule would work, well, that would be okay. And so what we're going to do here is we're going to take one of these two offending terms right here, and we're going to rewrite that so that that's now in the denominator. If we had x log x, that would actually be the same thing as log of x divided by 1 over x. Right? Here, you can prove it to yourself by going, we can multiply this way, those would cancel out, and we get back to x log x, right? We've moved the x to being down in the denominator like that. In other words, this limit right here is the same thing as the limit as x approaches 0 from the right of the natural log of x divided by 1 over x. Isn't that feel a little bit like a trained dog at a dog show jumping through a hoop? Yeah, it kind of does. That's quite the little trick we just did there. But by doing it, look what we got here. The natural log of, if we just tried direct substitution, natural log of 0 is negative infinity. Plug in here is 1 divided by 0 is infinity. We got another infinity over infinity problem. Now, L'Hopital's rule is going to work. So we can go ahead here and have a L'Hopital's rule and say this is going to be the same thing as the limit as x approaches 0 from the right of, oh boy, time to see if you remember things. What's the derivative of natural log? 1 over x. What's the derivative of 1 over x? I believe it is 1 over x squared, is that right? Minus 1 over negative, yeah, there you go. And with a little rearranging, you can see that that's the limit as x approaches 0 from the right of negative x. Now let's try direct substitution. Just put 0 in for x. Oh, it's going to be 0. Well, so apparently this original limit here is just equal to 0. And I did the derivative down here. I mean, I made the graph of it because I never trust, down here at the bottom of page 5. And the graph of this function, x natural log of x, looks something like this. And as we approach 0 from the right, we are getting closer and closer to the function being equal to 0. As x gets closer to 0, the function is getting closer to 0. It's pretty cool that those kind of tricks work. And actually, there's a whole bunch of these kinds of tricks. And is there more? Yeah, of course there's more. There's always more of these things. There are actually quite a few of these indeterminate forms that L'Hopital's rule can be used to solve, but we're not going to do all of them in this class, just in the interest of time and the world right now. Another kind of problem that you can come up with, another indeterminate form, is if your answer is in the form of infinity minus infinity. What does infinity minus infinity mean? I mean, infinity can be different sizes. They're all infinitely big, but this is hard. It's hard to know what this means. Let me give you an example, and we'll see how we'll use L'Hopital's rule to do it. This is 442 in your book. And it's asking about the limit as x approaches 0 from the right of the function 1 over x squared minus 1 over the tangent. Well, again, as should always be your guess when you're doing problems that involve limits, try direct substitution. Well, 1 over 0 squared is 1 over 0, it's infinity, minus 1 over tangent. Tangent of 0 is 0, so you've got an infinity term minus an infinity term here. Well, you can't directly use L'Hopital's rule. It'd be great if you could just take the derivative, but it doesn't quite work. We have to get it into a form where it's either infinity over infinity or 0 over 0. The strategy when you have these ones that are subtraction like this is to find a common denominator. So like on this one here, we're going to find a common denominator for this thing. It's going to be 1 over x squared. We're going to make our common denominator x squared tangent x. So we're going to multiply it by a fancy way of saying 1, so that this term now has x squared tangent x in it. And on the second term, we're going to multiply it by another fancy way of saying 1, which doesn't hurt anything, but it gives it tangent x times x squared. Now we can loop those two terms together. They have a common denominator. And we have in the numerator tangent x minus x squared all over x squared tangent x. Now, is that a L'Hopital's rule thing? Let's see here. Tangent of x is 0 minus 0. Okay, the numerator is 0. Denominator, x squared, put the 0 in for x. Well, it's 0 times something, who cares? This is another 0 over 0 problem. Now L'Hopital's rule comes to the rescue. Alright. So we're going to apply L'Hopital's rule here. L'Hopital's rule tells us that we can have that same limit, but take the derivative of the top and the derivative of the bottom. Derivative of the top is secant squared x minus 2x all over, let's see, that's a product rule. 2x tangent x plus x squared secant squared x. Well, that's ugly. But, well, okay, it should smell a little bit like direct substitution time. And if you plug in direct substitution here, it's a little bit of a mess. Let's see here. Let me double check here. The numerator of this will be equal to 1 by direct substitution. And the denominator of this will be equal to 0. Okay, I'll leave it to the viewer to go ahead and plug in these numbers, put some zeros in here and see that this one's equal to 0. That's actually easier to see. And that this one is equal to 1. We got a weird thing here, but that's not one of the indeterminate forms. That's just undefined. We know that means it's blowing up. And in fact, in this case, it is blowing up to positive infinity, and the text of your handout explains how you can tell that. Now, I will not try to draw the crazy graph that's there at the bottom of page 6 of your handout. That is the graph of this original function up here, and it's a mess. But, as Desmos shows you, as you approach 0 on the x-axis, you can see the function is blowing up towards positive infinity. So this original graph here is blowing up towards positive infinity. Now, these are not the only indeterminate forms that L'Hopital's rule can help us with. L'Hopital's rule has some other great possibilities, like 0 to the infinity power. I mean, 0 to any power should be 0, but what about 0 to the infinite power? I don't know. Or how about infinity to the 0th power? Any number to the 0th power should be 1, but what about something as big as infinity to the 0th power? These are two more examples of indeterminate forms that L'Hopital's rule can solve for you. And the list goes on actually after that. I think though we've seen enough here that we can work our way through the problem set. I'm going to make sure that you don't have any of these weird ones that we didn't see on your problem set before I post it. I think it's going to be under control. Alright, you're going to have a homework set associated with this, and you have an exit ticket with it with a bunch of review type questions as we've been doing. I think you have everything that you need. Obviously though, I always like hearing from people with text and emails. Let me know what you need, and I'll get back to you. Alright. Take care of yourselves, and I will look forward to the video in a couple days.